web application incident preparation. So if you got your other, if you're looking online, the Adobe Flash log and traffic analysis. So here you go, 20 minutes. Yep.
Hello. My name is Sergey Bratus. I work for Dartmouth College. I'm a postdoc there. I'm going to talk about the tool that we made for log analysis, packet analysis. The idea was to use some really simple math and see how far we can bring standard tools such as Ethereal and those different syslog browsing tools that you see here and there. So these are really simple tricks. This disclaimer. I mean, it's really kind of awkward after the guys talking about guns to be talking about this, right? You can't really do much damage with that, or can you? Anyway, so there will be a bit of math. This will not be an academic talk. There will be no survey of literature. And this is not going to be about IDS, IPS online stuff. These are tricks for you to try offline, have the time. So some of those computations take time. I had to implement a user-defined function for MySQL, computing entropy of columns and various other things. So they take time. I hate programming in C. I had to for this. Entropy and friends. What can they do for everyday log browsing? I mean, log browsing is a chore, right? Packet trace browsing is a chore. So you look at this, the lines that you need, the packets that you need, are there somewhere, except they are maybe 20 screens down, each surrounded by a page of what you don't want to see. And what do you do with this, right? When you see this, the scroll bar being all the way a tiny speck up at the top, you have to deal with the uncertainty. You don't know exactly what's down there. You have to do some or your enemy is really this empty space in the scroll bar. So, uncertainty. There is actually a mathematical formalism for dealing with it, and that is entropy. People deal with uncertainty in Ethereal, in Wireshark, very simply. Click on the tab, sort it up and down, see the max and min value according to some sorting order, alphabetic most likely. Once you've done that, you can group values together, and you can use filtering. Drill down to the group of interest. So you've grouped records by IP, or port, or protocol, or any one of those countless protocol fields that are available in vectors and that you can make into a column if you close and then reopen Ethereal or Wireshark. I'm really waiting for them to implement it online so that you don't have to close out to bring in, say, some wireless primitive, say the wireless sequence number or some fragmentation bit. Anyway, the problem is where to start. There are hundreds of protocol fields. There are hundreds of potential columns. Which column or protocol feature to pick? And how to group. Sometimes, if you get that one extra column out there, you understand the data set immediately. But which one? So which grouping, which clustering helps you understand the data better? How to automate guessing the starting point and the best grouping algorithm? How to defeat that empty space scroll bar? And we just have to think about this mathematically. What's the deal? The deal is most lines in a large log will not be examined directly, ever. You will never look at every packet in 10,000 packet trace. It's just not going to happen. So you just have to find the interesting spots and to convince yourself that you've seen everything that's interesting, right? That you're not missing much, that your wonderful filter that grew to the maximum that the filter line can take is not actually filtering out something that you're interested in. So you have to deal with uncertainty about the rest of the log. And again, I'm saying this word uncertainty because this is what entropy stands for. Entropy is a measure of uncertainty. And I'm going to introduce entropy at the risk we have the audience. Okay. Old tricks, right? You look at any tutorial in data analysis, they tell you, look at the most frequent value, or look at the least frequent value, right? The things at the top or at the bottom in some sorting order, they are interesting. The middle, probably not so much. You can always find some projection, some feature where the interesting things will be either at the top or at the bottom. But if you have hundreds and hundreds of values, they are all equally distributed, you have an almost uniform distribution, what does it really buy you? Anyway, again, there are hundreds of protocol features. What if there are many columns, right? And what if there are many batches of data? Which columns to start with and how to rank them? It would be nice to begin with the easier to understand ones. And again, I'm going to say the simplest frequency distributions, the simplest histograms, which again I'm going to define in a minute, they are the best to start with. This is a claim, this is a heuristic, may not work for your log. If you can do it automatically, if you can automate picking that starting point, maybe you win. So your attention is this spotlight that you have to shine on the log, and you have only so much of it, it's small. So then you have to do it very carefully. You have to start looking in the right place. So here is this is a two-hand operation. There. So here is a modified ethereal. What I'm going to do is I'm going to load a packet trace. And you see it's a normal packet trace, about 5,000 packets, small enough. And here I have all the features that are available according to the ethereal dissectors in this set. So I'm going to use 802.11 MAC header features and IP just for kicks. So I've chosen these go into my. From these I'm going to select the extra columns. And here's an algorithm which I call the minimum entropy tree algorithm. It is going to build me a tree representation of this list of packets. And I'm setting the threshold to the most sensitive. Of course, in any real data set, you get garbage. And so you'll have to lower that sensitivity. But for now, I will keep it sensitivity. So it chugs through the records. It constructs a tree. And this is what I got. Right? And then I'll explain this algorithm later. So the algorithm thinks that there are two groups in the data. One record is really so different from the others that it makes sense to split them in just two branches. And all the 5,275 nodes, they go one direction, and one node goes the other direction. So that node must be special. Let's check it. So what is that node? I'm selecting it. I'm picking it in the packet list. I'm going to see it in the ethereal header. So what is this? Oh, it's IP, but the header length is 0 bytes. Yeah, that's special, right? So it's clearly a very different packet from all the rest. Okay, so I found an anomaly. So again, this algorithm is adaptive. It doesn't have any knowledge of what these columns stand for. It just goes by the distribution, by the frequency counts of distinct values that you encounter. So here's the next. Oh, there is some fragmentation. So most of the traffic is unfragmented, but there are 3 fragments. And they go into 3 different branches. Now, for a moment, let's just look at the convenience thing. Here, I double-click on the top of the tree, and I see the distribution of the unique values under this node. So I know that in this subtree, I have 3,130 unique values of IP ID and 2,967 values of the sequence number of the MAC of the 802.11 MAC header. Why less than the IP ID? Well, there are actually some retransmits. So if I look at this distribution right here, I see that there are 13 counts of this value, 1380. So I can actually mark these records here and see where they go. And I can actually rebuild my tree, say, by IP source, resplit it, and see where these 13 records end up. So here, here. So these packets, these source IPs led to retransmits. So, you know, I'm operating on the tree and on the histogram, except you probably don't see that this is a histogram. I'll have to convince you. Anyway, so standard tricks, right? How do you look at your ethereal? You click, you sort you click on the column headers, you sort, you see the ranges. Okay, so the destination IP in this particular set goes from 192, 168 to the same thing, 10.100. The destination port goes up to 8100 and starts at 1. What is TCP port 1? Does anyone know? Does anyone remember? Yep. So here in the audience is the person who taught me that. Wave. Anyway, now we have hundreds of those potential. How do we choose? Just ranges are not enough. So let's take a look at a column. Count the number of times each value occurs. See, here is, oops. See, here is www port 80. This is the column for the destination port. You don't have to, of course, you don't have to see that column to do the computation, which is the whole idea. So 2 counts of port 80, then port 445 for Microsoft DS, right? So the histogram then would have a column whose height corresponds to the count of that value. So having done it for this column, we know that most of those records in that batch we just loaded are packets directed at port 45, the tallest column, right? The tallest column. And then there is some port 80, and then 21, and 1, and so on and so forth. So what is our uncertainty about the destination port? We are almost certain to get Microsoft-related traffic. And why is that?
Probability. The probability of the packet being a Microsoft product is
Yes. And so I'm actually going to introduce the concept of probability. Thank you for the cue. So I'm going to deal in histograms, right? I'm going to pick the simplest histogram, the histogram on which the top and the bottom frequent values are easy to see, are easy to spot, that they mean something. They hardly mean anything on this graph, which is the source IP. Well, that's probably randomized anyway. Right? So let me take the counts of these ports, right, and divide my entire packet series into bins. So N1 is the count for the bin with destination port equal to 445, the most populated bin. Then they reseed. Probability is the fraction of the total number of packets that ends up in this bin. So the probability that I get something sent to port 445 is the count of packets in that bin that the filter would bring me over the total number of all packets, right? If I were to draw a random packet with my eyes closed from that bag of packets, then with a high probability, with a really high probability, I would get that it's a Microsoft DS packet. So then, entropy is going to be a one-number measure of the histogram. And it's defined as follows. You take all those probabilities, you count the number of things in bins, you divide them by the total, and I by, right? And you add them up and multiply them by the log of the inverse probability. And for some interesting reason, you know, one of the fundamental laws of nature, actually it's a law that is really, really close to you, to your day job, right, or night job. It measures the lack of information about the values of the variable. It is related to the number of bits needed to encode this to full certainty. So why does it work this way? Here's a very simple example. Here's a fact of life, right? The least number of bits needed to encode numbers between 1 and n is log base 2 of n, right? We're all on the same page. Everyone agrees, right? You want to encode the number between 1 and 100, you need log base 2 of 100 bits. Now, if you are to receive one of n objects equally likely to be chosen, say it's your birthday, right? And you have a rich uncle. He might give you a bicycle, a Ferrari, a new computer, anything, right? And he chooses absolutely randomly. What is the measure of your uncertainty? Claude Shannon, who started this whole, who founded this whole theory discipline, gave the answer along the lines of the number of bits needed to communicate which object you are getting. Let's say the number of the object. They're all numbered, right? Ferrari is number 1, the bicycle is number 2, or probably the other way around. Is the measure of the uncertainty. This is how much information is missing, is needed to complete the picture and take all of the uncertainty away. Now, if some object is more likely to be chosen, say it's mostly bicycles and very seldom Ferraris, then the measure of the uncertainty decreases. The measure has to follow. So here's how this works. Here are 4 objects, right? Bicycle, Ferrari, something and something, right? The probability of choosing them is uniform. Probabilities have to add up to 1. The entropy formula will give us 2 bits. Yes, a number from 1 to 4 can be encoded in 2 bits. 2 bits are enough. Now, I bias the scale. Now, in half the cases of all, I will draw object 1, and then objects 2, 3, and 4 will follow with receding probabilities. The entropy decreases. It's 1.6 bits on average. And I'm not going to go into just how averages goes into the computations and the definitions. Obviously, you have to imagine that this happens not just one time, but many, many times. And we're encoding the average case, the stream of such presence. Now, let me bias it even further. In 80% of cases, you get object number 1. Your uncertainty still decreases. You need just a bit more than 1 bit to take most of your uncertainty away. Finally, if it's only bicycles, then your uncertainty is 0. That's what you're getting, right? So that's what entropy is. This is how it behaves. The entropy of having only one value, perfect knowledge, is 0. Well, when all n values have the same frequency, entropy is maximal, and it's log n. And for everything else, it's in between these bounds. So now, for each histogram, I have a one-number measure of the uncertainty of this associated distribution. So here, that summarizes this column for me. There, that summarizes that column for me. And so I have, in the next slide, 1.07 for the destination port, 5.79, and 6 for the destination and source port. That's how it goes. Pick the simplest. Start with the simplest. That's how we got the weird zero-length IP header to begin with in the original example, right? That is how that tree got constructed, recursive down. So you're likely to get your data arranged in, well, here it is. You're likely to have your data arranged in the tree that's not very branchy. And just a few of those branches, when entropy is low, are going to carry the weight of the distribution. Everything else will be the tail. So you'll get very biased histograms. You'll get the columns picked, which have very biased histograms, where the top level value, the top frequency value and the lower frequency value make more sense. So you don't know what anomaly you're looking for. This is called, I call this anomaly browsing. You'll know it when you see it, right? You know about IP header length of 0 being bad. You'll know it when you see it. However, you have to find the smaller haystacks, a succession of smaller haystacks. That saves you time. More old tricks. Look for correlations. If two fields, if two protocol features are correlated strongly, but for some values the correlation breaks, look at those. So if a user comes from the same IP, right, or if a particular length, packet length, corresponds to a particular call, or a particular TTL corresponds to a particular application. Scoreboard for last year's DEF CON. Was it last year's DEF CON or the DEF CON just before that? When people were able to determine that the scoreboard, which one the scoreboard machine was, and could tell by the TTL the fact that this was the scoreboard visiting their and not the competitors. That's how I heard the story, right? Sorry? Now, if it's a quick question.
So aside from this, the plugin for Ethereal and Wireshark being fairly cool looking, how is this different from what CMDS did?
Tell me what CMDS did.
Was it computer misuse detection system was originally implemented by what was it? Something for the government got turned into purchased by CA, got purchased by Secure.
Yeah, okay, I get the question. So the short answer is, I haven't seen this heuristic applied to log browsing. So I haven't seen displays being constructed with the use of entropy. People certainly have used entropy for IDS, IPS, host intrusion detection, with all the false positives that this brings. And I really can't guarantee that an entropy-based approach in an IDS, from the point of view of false positives, would work better. But when you're interactively browsing, you have the power to control it. You have the power to correct it. So let me return to correlations and pairs of field values. Which pair of fields to start with? Where to look for correlation? How to rank those correlations? Too many to try by hand, even if you have R or MATLAB. And so the answer will be conditional entropy. Again, I'm going to look at histograms, only they will be two-dimensional histograms. So source IP on the x-axis, destination port on on the y-axis. On the z-axis, the count of the co-occurrence of IP and destination port. So at that point, this is the count of this source IP and this destination port co-occurring in the packet. So two-dimensional histograms. And this being a distribution, you can compute its entropy, right? It's now squared the number of values, but they're values nonetheless. You can still derive probabilities of the two events co-occurring. You can still derive total. You can still compute the entropy. There is this thing called conditional entropy. And I'll ask you to believe me that this is what quantifies how much uncertainty remains about y when we know x. If we know the TTL, how much do we know already from this data set about the destination port or destination IP? Compute those things, rank them. It will take time for all pairs. You need C. This is how you get the next levels of this tree constructed. And mutual information is just another spin on that. How am I doing on time? Okay. So these are the histograms of a standard port scan alerts, actually, from Snort. And so I see here the pair for the destination port, destination IP. Here is the pair for the source port and destination port. Oops. I'm giving the ending away. Source IP and destination port, all the pairs, right? Which histogram would you start with? Yeah, well, too bad. Typical finger slip. Anyway, well, I would look at this peak, actually, because this peak suggests that, on average, this pair is rather uniformly distributed. And yet, there is this very strong correlation between these two particular values. So that certainly is interesting. That certainly deserves being looked at. But if I compute the conditional entropies, how much we know about how much uncertainty remains about y once we know x, how much uncertainty about the destination IP once we know the destination port, I would go with this one, yes. And it disclosed its own identity. And so you end up arranging your data in a tree, right? Trees are all around us. They get in the way of microwave. We get to see them everywhere. They are, they crop up in all sorts of algorithms. Your IP tables policy is a tree, right? You have decision trees embedded in pretty much any procedure that you follow day to day. So here's a way to bring trees into, well, packet analysis. We implemented this for syslogs as well. So there is a little utility that parses syslogs and actually comes up with patterns that are likely to apply to your syslog if it's an unknown format. Parses out those usernames, TTY numbers, source IPs, and so on. And you can apply it, and this is the tool that did that. You can apply it to practically any kind of data that can be neatly created. And by the way, here, by this heuristic, we see that peak in red because it goes against the statistical tendency of the pair. And the rest is just screenshots, which you have already seen in action. So you can switch between these two plugins, between these two views, find the packet in tree view, and switch between the different views. So information theory provides good heuristics for summarizing the log data, in small batches because you have to do a lot of computation to bring these heuristics to bear. It builds useful data views, and it finds good starting points. And it's fat-fingered, and it's a part of a complete analysis kit, also known as breakfast.
Excellent. Thank you, Sergey. Sweet, sweet source code. All right. We're going to take about a